It's great to be here at the AI and Big Data Expo talking with yourselves about the business end of IT. So we've got some interesting technology to talk about today. We're proposing to use and as part of this presentation to gain interest in order to partner up with interested people like yourselves. So you may be a potential investor, an IT decision maker, a startup entrepreneur or media executive, or even a tech provider. The purpose of this presentation is to give you some background, some use cases, foster discussion with a view to a more serious discussion about becoming involved in the business and the technology. So, generative adversarial networks, or GANs for short, are a pair of models or neural networks that run in competition to each other. First proposed by Ian Goodwin in 2014, he postulated that given a training set of data, these two models would compete against each other and learn from each other using adversarial training and backpropagation. So, in a GAN, one neural network learns to generate data similar to a given training data set, and the other calculates the probability the generated data is fake. These two models are trained together, where the generative model captures a data distribution, which is our training sample, and a discriminative model estimates the probability that its input came from the training data rather than the generative model. This approach is called adversarial training, which is where inputs are chosen by an adversary. Thus, the discriminator is indirectly training the generator each time it rejects a sample as fake. In other words, one neural network tries to generate data based on a training sample, and the other neural network tries to figure out whether its own data input is real or fake. The analogy used by Ian Goodwin is that of a counterfeiter and a cop, where the counterfeiter is continually trying to forge copies of a painting, and the cop is continually trying to distinguish the forgeries from the real thing. The counterfeiter is the generator, and the cop is the discriminator. As each successive painting copies are generated by the counterfeiter, the cop decides whether the painting is fake or not, based on the original sample. So indirectly trains the counterfeiter to make better copies until it finally can fool the cop. This is the core of why it is called adversarial training. The cop is training the counterfeiter in an adversarial process. The core purpose of a GAN is, given a large set of data, the GAN is capable of generating unique data that is effectively indistinguishable from the original. Our objective is to use this technology to create new content like images, videos, and virtual reality content that is indistinguishable from the real thing. So why do we need to know about GANs? We need to know about GANs because they're having an impact on our society, some in a good way and some in a bad way. GANs can be used to create art and music, make photos appear sharper, synthesize voice and video, or do drug research. GANs can also be used maliciously to fake videos, crack passwords, and fake voices. The most famous use of a GAN was the faking of President Obama making a speech which he never made. This is why we need to understand GANs. So how do GANs work? Taking a neural network view, we can see here some GAN course material from Google as our example by breaking down how the discriminator and generator work. In this example, the generator learns to generate plausible data based on a training sample set and some random data input. The random data input introduces variations into the output that the generator produces. The discriminator uses the output from the generator as its input via the sample box, and through a process called backpropagation provides a signal to the generator to update its weights, which essentially trains the generator with each pass through the process. Backpropagation is a method used in neural networks to minimize the training error, whereby a calculation allows the weights associated with the network to be updated backwards each time a pass is made based on its forward pass. The two sample boxes feeding into the discriminator represent both the real data, which is our sample, and the fake generated data. The discriminator connects the two loss functions. A loss function is a measure of how far a model's predictions are from its label, or to phrase it differently, a measure of how bad the model is. During discriminator training, the discriminator ignores the generator loss and just uses the discriminator loss. The discriminator classifies both real data and fake data from the generator. The discriminator loss penalizes the discriminator for misclassifying a real instance as fake or a fake instance as real, and the discriminator updates its weights through backpropagation from the discriminator loss through the discriminator network. During generator training, we introduce random input or noise, which allows the generator to create variations with the sample, and it trains using a similar method of backpropagation. So bringing it back to our counterfeiters and cops analogy, as the generator improves with training, the discriminator performance gets worse because the discriminator can't easily tell the difference between real and fake. If the generator succeeds perfectly, then the discriminator has a 50% accuracy, which is just the flip of a coin. This is called convergence. So in terms of technology maturity levels, GANs are still pretty new, as they were only first proposed in 2014 by Ian Goodwin as a method of addressing issues with similar networks. But since 2014, GANs have been extensively used in various research and prototype projects, with each successive technological advancement overcoming problems and testing the boundaries of what the technology is capable of. GANs are still in the early technology phase, or as Gartner puts it, the innovation trigger phase. But as more users enter the ecosystems, GAN technology will mature into more mainstream use. The technology risk associated with GANs working as intended has successively decreased from when they were initially proposed in 2014. In fact, with GANs evolving from the wider development of neural networks since the 1950s, it would be safe to say that GANs have been built on solid foundations. Regulatory risk is another factor that is relevant here, as the abuse of technology may require government to pass legislation which enforces compliance. So some of the problems associated with GANs include the malicious use of the technology for purposes like generation of fake images and video, as we've seen with the fake Obama video. They've been used for password hacking. Voice cloning has presented itself as another issue. On the technical side, GANs sometimes have problems counting the number of eyes in an image of an animal or a person. There's also something called non-convergence, where GANs miss entire modes from the input data. And in general, AIs can suffer from something called algorithmic bias, which in the past has caused classification of images of African American as gorillas. Technology risk mitigation for GANs relies on a number of elements: the ongoing R&D, refining models, building of prototype and MVPs, the availability of AI-specific hardware and solutions from major vendors like NVIDIA, Google, and Facebook, plus the partnering of different stakeholders from universities, big tech, and other organizations further mitigate this technology risk. So I think it's safe to say GANs are here to stay, at least for the next few years. So what can GANs do and what can't they do? Well, GANs can create new content, but only with training samples and backpropagation. They can do next video frame prediction or image-to-image translation by creating new faces. Also, they can do lip-syncing voices with video and create the video, as in the Obama video. They cannot create new content without a training sample. So for example, they couldn't create a cityscape sunset without prior training samples and backpropagation. So what problem do GANs solve? Well, computers have had an issue with generating new data. Even the ability of a computer to generate random numbers is limited as they still have to be programmed. Content is expensive to generate. Creating an image, recording a video, writing music, or recording audio takes time, effort, and money, so can be expensive. In fact, recently, GANs have been proposed for use by voiceover actors who don't have the time for all their clients and instead use an AI GAN solution to simulate their voice for commercial use. More proposed use of GANs include text to video, but why stop there? Why not go from voice to video and fully automate the hands-free creation process entirely? So GANs can address these two main problems by generating entirely new content and thus creating valuable IP, and secondly, they can do it faster and cheaper than the traditional method. So essentially, the problem they solve is time, money, and effort. Likewise, video, images, voice, music, or even virtual reality content all need to be created. Virtual reality programs are expensive to design, and gaming content costs extraordinarily high amounts if they're to be brought up to levels required for commercially acceptable quality. The opportunity is to be able to generate these types of content fast, efficiently, and with a high enough quality to pass the sniff test and therefore commercial use. The opportunity now is to get in early and establish a niche beachhead as an early mover, build IP, develop ubiquitous applications, and develop some unique business solutions. The market for images, video, and VR is a multi-billion-dollar global industry spanning across countless sectors, with the VR sector alone worth $22 billion in 2021. Video streaming is worth $60 billion, and video advertising is worth $35 billion. Music streaming is worth a measly $13 billion. Some of the customer benefits include faster generation of content, cheaper licensing of content for the commercial market, can be trained with real-life examples so realism levels are high, and also they can simulate realistic scenarios in real time, especially for adversarial training. So the customer target market includes people from operations, management, and IT from a host of industries, including government and military, IT providers, hosting systems integrators, media and advertising, corporates and industrials, big tech, technology enthusiasts and entrepreneurs, and essentially nearly everyone who has a touch point to multimedia content. The use cases below are relevant for our discussion, as each of these discrete projects validate GANs for further advanced use in multimedia content generation. We have face generation, this person does not exist, where anyone can go to that website and see a completely new face generated every time. Deepfakes, the Obama video showed that voice and video can be synthesized and overlaid with each other. It created a watershed moment for video and voice and begged the question that will anyone trust video? And if they don't trust it or they do trust it, can it be weaponized? Also, short film generation by AI GAN demonstrated where an AI used 11 different GANs to create the entire production process of a short film in under 48 hours. Video image compression and next video frame generation push the technological boundaries of how GANs can be used with video. Voice cloning of actors now allows voices to be sampled and reused without the actor being present. And text-to-video generation shows how simple stories can be dynamically converted into video. This allows us to take GANs to the next level, which will enable better commercialization. So our proposed use cases can include generating video or VR training scenarios for emergency, corporate, or military use, where buildings, objects, and landscapes are dynamically created for simulation training based on a textual scenario or architectural plans. We could also create entertainment, TV, movies, or games. Advertising also can be created based on target profile characteristics, bias, or preferences, all on the fly and dynamically. Voice generation for voiceovers, or image generation for commercial licensing. So here's our call to action for you to become involved. Gartner predicts 5 to 10 years mainstream use. We predict our ROI timeline to be a little shorter, 3 to 5 years to be able to generate realistic video and VR advertising in real time based on target viewers' consumer preferences and market research when using text to video or voice to video. 5 to 10 years Generate realistic VR training scenarios in real time for emergency workers or military operators to practice while in transit to the location. 10 to 15 years time, generate a feature-length movie based on your liked movies and your favorite genres and movie stars. 20 plus years time, creation of cybernetic animals and humans based on users' past pets and sexual partners. So come and talk to us for a confidential discussion if you want to become involved.